So the big picture is that in arbitrage pricing theory and generally in finance, we think that securities earn higher expected returns because they're more exposed to some sources of risk, right? In particular, APT says that these sources of risk should be systematic in nature because otherwise you can diversify them away. Conversely, the expected returns of diversified portfolios that hedge all the systematic risk should be zero or very close to zero. Obviously, these are limits result, but we should expect some consequences in finite samples. Of course, APT is the foundation of empirical multifactor models for the cross-section of returns. So why is it hard to test APT's implication? The first problem is identifying the common factors, right? There's always the issue that whenever you find alpha with respect to some portfolio, well, we can say, okay, but maybe we haven't found the right factors. Once we find the right factors, we'll be able to explain all of these return patterns. Second, expected returns are unobservable, right? So what we're going to do is we're going to combine three different techniques. So first is an efficient method to measure individual stock dynamics exposure to every common latent factor, which involves a singular value decomposition of the return matrix. No need to estimate the covariance matrix. No need to estimate the factors. You could do so if you like. The second is an out-of-sample measure of expected returns. We're going to use a broad set of public and firm-specific signals. We're going to do rolling regressions to predict out-of-sample returns. And we're going to do this using both machine learning methods and linear regression methods. Finally, we're going to use pure plays to hedge all the systematic risk while sorting on expected returns. Our main findings are that portfolios that hedge systematic risk perform better than similar portfolios that take more systematic risk. Now, this sounds very puzzling from a finance theory perspective. Why is this the case? It's because latent factors explain a considerable fraction of the time series variation of stock returns, but latent factors exposure doesn't carry a big risk premia. Latent factor exposure carry negligible risk premia, and as a consequence, the latent factors exposure cannot explain almost any of the cross-sectional variation in excess returns. This is going to lead to some very puzzling profitable trading strategies with zero ex ante systematic risk. All of our portfolios are going to be forming so that they're tradable. So of course, there's going to be some out-of-sample variation. Yeah. There's a lot of related literature. A lot of people in the room have made wonderful contributions to this. We're going to add to the factor models debate the cross-sectional return prediction and the characteristics versus covariance. In the interest of time, I'll have to skip the list of papers, but we're building on the shoulders of very, very nice research. So just to fix ideas, APT says something simple, right? APT says that the expected return should be driven by an average return plus some factor exposure times the factor realization, plus some idiosyncratic noise. Now, the expected return should be can be driven by a mispricing component, an alpha, if you will, plus some price of risk that correspond to the exposure to the factors, right? The idiosyncratic risk is going to be unrelated, covariance is zero, and then hopefully, and this is the only punchline, is that alpha should be zero, right? There should be no expected returns in excess of the systematic compensation. Because otherwise we can build diversified long-short portfolios with very, very high Sharpe ratios, right? Because, just briefly, the realized return of a long-short portfolio is going to be the difference in average returns plus the difference in betas times the factor exposure plus some noise that just goes to zero if you use enough number of assets, right? It turns out that if this factor exposure is equal by construction, for example, then you end up with only the alpha differences in returns, right? This difference should be zero because otherwise the Sharpe ratio of the portfolio is going to grow relatively quickly the more stocks you have. Yeah. So of course, what we're going to try to do is we're going to come up with a zero-cost portfolio with high average returns, zero systematic beta exposure by construction, and we need two things. We need the expected returns, which we're going to get either using predictive regressions or machine learning, and we need the covariances. So we're going to use high-dimensional covariance estimation. We're going to forecast the returns at time t plus 1 using a subset of variables at time t. We model the condition expectation as a possibly nonlinear function of characteristics available at time t using random forest regression, but similar results obtained with a linear regression or Lasso methods, or essentially any reasonable forecast of returns. It's an out-of-sample prediction with similar structure as rolling regression. We feed the nonlinear function up until time t, and then we forecast using those variables. Standard stuff. We use the past 5 years to predict the next month, so we're using rolling window estimates. Supervised machine learning, the way I want you to think about it is a prediction machine. It just gives you it receives the public information available at this time, and it returns a forecast, right? And of course, the best forecast available is the conditional expectation. And what machine learning is doing is just a flexible way to approach these conditional expectations. Could you use linear regressions? Yes, it also works. We're going to use the conditional betas. Betas with respect to the latent systematic factors to absorb as much of the undiversifiable variation as possible. And we're going to use 1 year rolling windows of daily returns to address time varying betas. Does this work if you use 3 years rolling windows? Yes. If you use 5, yes. So how to avoid the covariance estimation? This is just a little bit of linear algebra just to keep everyone on the same page. If we think that RT is the mean matrix of daily excess return for the past year, so 255 days times, 4,000 stocks, then if you recall from your linear algebra classes, the singular value decomposition is going to be USVT with U prime U equal to V prime V equal to identity matrix, and S diagonal, right? That's just the linear algebra. Covariance matrix, the usual one is just 1 over n r primes r with size n times n. And it's going to be, of course, very singular if n is greater than t, 4,000 stocks, 255 days. You cannot invert that. Doesn't really matter. Again, the composition of that covariance matrix is going to be V S squared V transpose. You can trust me on that one, or you can do the math. And the principal components, the usual one, the classic latent factors are just going to be RV, right? And of course, the covariance of the returns with the principal components is just going to be V, the exposure, times lambda, the average risk, right? And the variance principal components is going to be lambda. And the punchline is that the betas, the usual latent systematic betas, with respect to the factors, are contained in the V matrix. If you remember, you can just obtain this V matrix directly from the singular value decomposition. So, just keep all the steps, no need to covariance estimation. The covariance cannot have more information than the return matrix because it's just a linear transformation on it, right? So we just do that. Now, just one caveat is that whenever you're thinking about the covariance matrix, that's a realization in sample, right? So what we can do, because we're very careful with the out-of-sample forecast in order for this to be tradable portfolios, we have to predict the realization in some sense. Now, lucky for us, betas are very, very persistent relative to realized returns. So what we do is we forecast the next month using the past month, right? We use a panel regression AR12 model. Why 12 flags? Well, because we use 1 year, so it's kind of like to disentangle the covariances, to disentangle the autocovariance. Right? So this is extra because a lot of wonderful discussants, including Brian, that I don't know if you're here, have been suggesting, okay, but what if instead of using this high-frequency data, you use characteristic-based betas, right? So characteristic-based betas, and I promise I'm close to being done with the theory, is that you have alpha is equal to beta plus the factor exposure. Just in this case, you're going to model betas as a linear function of characteristics, right? So beta is gamma prime z, where z are some characteristics. Alpha is gamma alpha z when z are some characteristics, and you end up with your model z gamma alpha plus z gamma f, right? Now, what you can do, and this is from a paper with Nick, is if you just multiply the whole return structure by z prime z minus 1, then you can basically cancel out things, and you end up that the projected returns on the space of characteristics, the managed portfolios, are going to have like gamma alpha plus gamma times the factor return plus some idiosyncratic noise component, right? The punchline is that if you subtract the average return from this, you can exactly recover the factor structure from this factor, right? So we are also including those characteristic-based covariances. So of course, it's just the characteristic-based betas are just going to be the singular vectors of the managed portfolios, and of course we calculate them using rolling windows, and we forecast them using a 3-year rolling AR12 lag panel model to obtain out-of-sample results. So far, proxy for conditional expected returns for every stock at every point in time. But it's already getting interesting. Betas with respect to the latent factors for every stock at every point in time. We want diversified portfolios sorted on expected returns with a beta of 0. How are we going to do that? We're going to use pure replace, right? So if you just look at equation 14, if you minimize 1/2 of W prime times W without any restrictions, the result for that would be 1/n. That's the maximally diversified portfolio, right? In this case, we're going to add some restrictions. So maximally diversified portfolio subject to being 0 cost, and subject to these portfolios having some expected excess return equal to some value, and subject to, most importantly, the betas being equal to 0, exactly 0, right? Now, these are the estimated betas that we have from our forecast. You can just collect those things into a nice A matrix, with iota, which is a vector of ones, with mu, which is your vector of expected excess return from either your linear model or your machine learning, and your matrix of betas that we estimated both using the high frequency returns, the daily returns, and the characteristic-based model. The punchline is that the weights of this diversified portfolio is just it's going to look awfully lot like a linear regression. So it's going to be A times A transpose A minus 1 times A, where A is defined that way. And basically, it's extremely close. It's actually, without any normalization, there's going to be exactly the slope coefficients on the Fama-Macbeth cross-sectional regressions of returns, on the expected excess return, a constant, and the betas. Right? So these are very easy to get. In practice, we're just going to normalize this such that the absolute value of the short side is equal to -1, and the absolute value, and the value of the long side is equal to 1, so that these are comparable with traditional models. Yeah. We're going to use CRISPR monthly and daily returns. We're not going to do anything fancy with that. Standard data, composite data set, 1965 to 2021. Now we actually have an extended sample, but I will not present it today. We're actually using predictors from Freiberg, Neuhel, and Weber. We added some variables lately. I'm also going to show some exercises. Yeah. So the factors are latent. And to study them, we project them on the returns space using pure plays. And the important thing is that we do not care that much if the factors themselves are priced, rather whether the exposure to these factors are priced, right? The correct way to do that would be a cross-sectional regression of returns on a constant plus the betas, right? Those are going to be the zero-cost portfolios that are Fama-Macbeth, right? If we make them unit cost, then the portfolios are going to be related with the market. And if we use some kind of version of the weights being proportional to betas, then the variance is going to be extremely large by construction, right? Because these latent factors are supposed to absorb as much variation as possible. So as usual, we use pure plays. We minimize W prime W subject to being 0 cost. W prime vector of 1 is equal to 0, iota. Subject to the factor J is going to have a beta of 1 with respect to its tracking factor and beta of 0 with respect to the other ones, right? And this is going to be exactly the coefficients of the Fama-Macbeth cross-sectional regressions, but they're going to be normalized so that the short side is equal to 1 and the long side is equal to 1 in weights. Mm-hmm. Yeah. Now the variance is explained by the principal components. So in sample, the best way that you can explain the covariance structure is using the principal components. That's just a mathematical identity, right? The question is, how good are we capturing this variation out of sample, right? So this is the in-sample one. It turns out that even in sample, it's just the whole cross-section of stock returns is very high dimensional. Unsurprisingly, we're using individual stocks, so you need 50 portfolios to get 40% of the variation and 100 to get 50% of the variation. Yeah. The interesting thing is that if we reconstruct our factors, actually using the estimated betas instead of the in-sample betas, we get actually pretty close stock return reconstruction, right? The intuition is that betas do not change as fast in the monthly level, so you're basically capturing good variation. Now, the cumulative log return of the zero latent cost factors, and the way I like you to think about the zero cost factor is that the first factor is being long on stocks with high beta and short on stocks with low beta, right? With respect to that specific factor, the second one is being long on stocks that are very much exposed to the second factor and short on stocks that have a negative beta with respect to the second factor, right? The interesting pattern that we observe is that none of this factor exposure is being priced. So the cumulative returns are very close to the risk-free rate, right? That's going to be problematic. If I just show you the statistic, the average returns are close to zero of the evaluated zero-cost portfolios. The Sharpe ratios are very small. In some cases, like very, very close to zero. None of the T statistics is significant, so it seems that none of this factor exposure is being priced. Can you construct the factors themselves in a different way so that they have some price? Sure, just a rotation, and if you make them unit cost, you can make them have a positive average return, although their CAPM alpha is still very close to zero. Now, the intuition is that latent factors will carry a high variance by design, like we're constructing them to absorb as much of the variance as possible, but they do not carry a substantial risk premium, or rather, exposure to these factors do not carry a substantial risk premium, right? So here's when things get fun. Hedging portfolios against all of these systematic risks will reduce their variation without reducing their returns. Now, that sounds extremely troublesome because, as I told you at the beginning, portfolios should only get high expected excess return if they have a high exposure to risk. Yeah. So, but interestingly, because none of this factor exposure is priced, the optimal thing is to hedge all of it, like completely all of it, right? So hedging portfolios against all systematic risk, against all the systematic risk that we can measure ex ante, is going to increase their Sharpe ratios by a lot. So these are the descriptive statistics of the portfolio. So just the market is in there for comparison. The average and standard deviation are for monthly returns, and the Sharpe ratio is annualized, right? So the market during this period has a Sharpe ratio of like 0.52. That's going to be the benchmark, right? The long-short portfolio, so if you just sort stocks on high expected excess returns minus low expected excess returns, has a high average return and a low standard deviation, right? With a Sharpe, so average return of like 1% per month, and standard deviation of like 4.3%. The Sharpe ratio is going to be 0.84. Now, this is still not puzzling, right? Because this portfolio's excess return could be explained by some factor. Could be explained by some exposure to some systematic factors. Now, the problem comes in what we call the beta-neutral portfolio. The beta-neutral portfolio is a version of the long-short that, in addition of like being sorted on expected returns, it's being hedged against all the systematic risk, right? How are we measuring the systematic risk? Well, we're using 50 principal components. Everything is out of sample. We estimate the betas, and then we hedge completely out of them, right? Now, this is very positive because we get an average return of like 0.92 and a standard deviation of 1.51, right? That's going to give you a Sharpe ratio over 2 in the whole sample. Can this be fixed in some sense by adding the characteristic-based betas? The answer is no. So actually, if you, in addition of hedging the 50 latent systematic factors, you hedge the 5 characteristic-based betas, you actually end up with a higher Sharpe ratio. Right? We end up with the same average return of 0.93 and a standard deviation of 1.40, right? With a Sharpe ratio of 2.31 during this sample period. The difference between the long-short average return and the beta-neutral average return is not significant. So I used to have a previous version of this graph. I updated the data set from a longer time sample in this time period, but as you can see, the Sharpe ratio is basically increasing in the number of factors, with the caveat that at the end of the 50, we have the characteristic-based portfolio. That's why you see a slight increase upward at the end. But the sensible thing that I want you to get from this picture is that none of these factors is explaining the returns, and just trying to hedge as most of them, as long as you can measure them accurately, is going to be very profitable. The cumulative log returns of these portfolios, well, the long-short looks like a great investment, but it has like some periods of volatility, right? The beta-neutral portfolio is essentially a smoothed out version of this portfolio. It's smoothed out because we're hedging all the systematic risk variation. There's an interesting pattern where roughly after the 2000, the predictability of these characteristics declines a lot, right? I'm just going to show you the statistics to see that even in that case, it seems like a good idea to hedge the factors, right? So if we look at the pre-2000 period, so 1974, 1999, 1974, because that's roughly when the composite sample starts getting larger, you can do this exercise for longer time periods, then the Sharpe ratio is going to be like 3.5, 3.84, depending on your specification, right? Panel C, which is the most recent period from the 2000 to 2021, you have an average return of the long-short of 0.48. So it declined a lot, right? And it actually has a Sharpe ratio of 0.29, which is not especially attractive. Once you hedge out this systematic variation, you end up with a Sharpe ratio of 0.91 in the specification. So that's still troublesome because it's almost twice the size of the market Sharpe ratio, right? So, puzzle still there, at least the predictability is not that more. In the interesting of the momentum context, I also want to try this. What happens if you just use the past returns to predict and you just use a linear model? So the simplest specification as possible, just taking past returns as predictors and using a linear forecast. Well, during the whole period, it works still very well, right? Like you still end up with a Sharpe ratio of close to 2 just by using this simple technique. If you break it down into subperiods, most of the return is constructed from the, it's due pre-2000 and post-2000, interestingly. The long-short portfolio sort of unexpected excess returns based on past returns. It's not really profitable, right? It has like a very, very positive, barely average return and, a Sharpe ratio close to 0. Now, when you hedge all of this systematic variation, you actually make the portfolio look profitable again, in the sense that the average return actually increases. So remember, you started post-2000 with just a mediocre forecast using the past returns, and once you hedge the systematic variation, you turn it into a profitable portfolio, right? What is the reason for this? The reason for this is, and we're conjecturing, and there's more research to be involved, is that a lot of the predictability due to past excess returns probably became closer to being a systematic factor in the sense of driving the covariance. Now, it wasn't a profitable systematic factor, so when you take this systematic variation away, you recover the predictability of this past return signal. Yeah. So I just want to remark that it's very puzzling because you get Sharpe ratios almost 4 times the market Sharpe ratio, of course, depending on the period, depending on the specifications. But this result look extremely robust, basically anything that we've tried, right? Now, the link with theory is both that, APT is going to have an extremely hard time explaining these returns because they're hedged against everything that we can hedge, right? And against consumption asset pricing based models, the Hansen-Jagan-Nathan bound is going to make it extremely complicated for consumption asset pricing models to explain this return pattern. I don't know how to get a Sharpe ratio of 2 in any model, 3 or 4. The latent factors cannot explain the returns. What about the reduced factor models? What happens if we regress this on, French 5 or Momentum or other portfolios? Unsurprisingly, the long-short portfolio is actually going to be able to be priced correctly sometimes, but the beta-neutral portfolio is going to be extremely hard to hedge. Yeah. So if we look at some time series regression, so I'm just doing a standard portfolio projection. I'm projecting the long-short portfolio at time t in the first 2 columns, against the market portfolio, right? So we see that the long-short portfolio already has like a big alpha of like 1.24 basis points percentage per month, and it's going to have actually a negative market beta. So, that's fine. Now, the beta-neutral portfolio, the t-statistics is in parentheses, right? So you get a t-statistic of like 7, right? The beta-neutral is in parentheses. So once you actually hedge the systematic variation, you get basically a beta of 0, almost as expected because the market beta is measured very precisely, and you get a t-stat of like 14. Right? The adjuster square is basically 0, indicating that at least towards the market portfolio, our beta-neutral portfolio is able to hedge almost all of the variation. When you try to project the long-short portfolio and the beta-neutral portfolio against French 5 plus momentum, you end up with interesting patterns. So you end up like, actually the French 5 kind of like decreases the average return of the long-short portfolio. It's loading, interestingly, in momentum, but the beta-neutral portfolio kind of like tries to diminish like this exposure, right? Not directly, because we're not directly targeting the French 5 factor betas. We're just trying to capture as much of the variation as possible, and as a result, the adjusted R-square goes from like 0.45 to 0.06. So basically, we're just barely picking a variation. The coefficient of momentum goes like from 0.58 to 0.07. So it's just barely some residual things, and again, the result explained because we're doing everything out of sample, so there's going to be some realized variation. What happens if we do this using the Q5 factor model or the Roberts sandbox portfolios? We're going to see a different pattern. Actually, in this case, the Q5 model and the Roberts sandbox model are actually able to price the long-short portfolio. So that's good for asset pricing, right? We want to be able to price these returns. But interestingly enough, once you hedge this beta neutral, you're going to get the usual result, that the explain R squared goes to 0, and the t statistics just blow up to like 10 or 12, right? What is the intuition for these results? The intuition for these results is that these models are actually capturing some systematic variation. So when you hedge that systematic variation, it becomes very hard for this model to explain them all, right? You just lose against this. So in some sense, at some point, I was hesitant to just put these tables because it seems kind of like we designed these portfolios to be neutral to everything. So it's unsurprising that they're neutral to everything, and as a consequence, they end up with a very high alpha anti-statistics, right? And just to conclude, so taking 0 systematic risk should produce 0 returns, right? That's what we started the conversation with. Now, along the lines, I think I convinced you that this is exactly not the case, right? This is not the case because the factor exposure is not price, so the optimal thing to do is to hedge it as much as possible, right? Try to measure the covariance as accurately as possible and just try to hedge all of it, right? As a consequence, you are going to end up with roughly the same average return. You lose some basis points, but you end up with like 50, 60% less variation, right? Not only variation, it's like systematic variation. So you also end up like less exposed to the business cycles. The Sharpe ratios are going to be 2 to 4 times as large as the market, depending on the sample and its specifications. And of course, this very, very much challenges the arbitrage pricing theory. Arbitrage pricing theory is a limit theory, but we believe that any finite implications is definitely not supported by the evidence, right? Obviously, this is also going to challenge consumption asset pricing-based models because the high Sharpe ratios just are very, very hard to explain based on the Hansen-Jaganathan bound. Popular factor models cannot also explain the returns almost by design because those models are capturing some systematic variation. So I guess the only good thing that we find is that the predictability seems to decline. Right. Thank you.
OK, let me first recap you the results. What's the main message of this paper? What we learned mainly from this paper? Let's look at this table. For a lot of you, it looks like a table. But to me, actually, it looks like a beautiful picture of Van Gogh to an empirist, really. Look at the numbers. Really amazing that at the far corner, you see great Sharpe ratio, 1.51 with beta neutral. Essentially, you neutralize all the beta systematic risk. You still get a very sizable alpha, sizable Sharpe ratio. That's really amazing. For those fund managers who try to get extra alpha, there's something here, potential for you. Okay. For me, as a researcher, for the extra alpha, the theory done really true. It's amazing. That's why the beautiful picture, the table is as beautiful as Van Gogh picture for me. Okay. Does really the paper answers this following question? Does APT really work? Well, what they did is to provide a counterexample. Here I provided an ex-ante tradable portfolio to show that it has no correlation whatsoever with all the systematic factor. And it earns extra risk premium. So it's kind of a using example to fight APT to say there is a problem for you. So I think overall, really, there is a thought-provoking paper. Okay. Basically, to academics, really tell us that our theory has some problem. It's hopeless for us to expect a few factors can explain all the cruxation of stock return. Cast the doubt of the form of 3-factor, 5-factor, or number of finite number, small number of factor models. Really, that we doubt their ability to work well in the real world. So I think it's really huge implication from the academic side. Again, as I mentioned earlier, well, to the practitioners, those of you here, hopefully that you get some really interesting idea to help you to get big, great alpha, or great paycheck, great better bonus for all of you. Okay? So that next time you'll be much happier to come to this conference. Okay? Okay. Now let me just recap to tell you what the idea of this paper is. I think it's a cool idea. Let me just summarize in a few key steps. First, you extract beta exposure. Okay, using covariance of asset returns. Assume there's a K-factor model in the world. Then I can extract all the betas of those factors. Then what do? Then use a current data, okay, to update your future, estimate the future beta. That's what matters for your next period correlation. Okay, they build an evolution model. Okay, then they use machine learning tools to forecast expected return. So 3 separate things which may not look like may not closely linked together, but then they put them together. Then use the portfolio optimization technique. These are familiar with all of you in the quant manager world. Now we've got all the portfolio optimization tools. Now make good use of it, then come up with the portfolio. Okay. So overall, I think that the paper really has a very clever idea, okay, which is really very easy to understand financially. So I think it's rich in financial intuition, and also very transparent. Okay, I think that's the feature of this paper. Now let me go through the details for you. Okay, without any questions, then I can have a lunch without meat, right? Now let's see what's the optimization doing. They're doing full optimization problem. First, let's say, okay, give all this estimation, betas, expected returns. Now here's what we do. We first get a zero cost factor from this optimization. You want to get a factor from the stock market, okay, with zero correlate to capture factor risk. Okay, that you have orthogonal to all other betas, but with the own beta is 1. So you basically capture factor. That's what's called a zero cost factor. Then also you can construct the 1 cost alpha, costing $1 to get the factor. So basically construct factor mimicking portfolio. So this is not the highlight point of the paper, but this tells you that what are the tools they have that can reasonably capture the factor you want. This factors looks like really pretty plausible. This is what the paper tries to show. You can get the APT factors, okay, approximation in the following fashion by solving the standard portfolio optimization problem. That's what you can do. Okay. Of course, here is got some question. As a discussion, we have given them some hard time. Okay, propose some questions. Okay, questions. So maybe some comparison might be interesting for you to do here, because here the paper provides a way to recover the factors. Then there are some other ways that recover factors too. Like you can use PCA, you can use the APCA or RPPCA versus PCA. Actually, also there's some Bayesian or older days like framework, which is written by Jan Gewicke, who's my advisor, and me. Then there's basically the versus ways of recovering factor. My question is that it'd be interesting really to compare what you recover with what other procedure recover, and maybe just to see what's some commonality. It's just an additional thing maybe interesting to explore. Okay, so that's my first really a question. Okay, I think the difference might help us to understand the role of timing beta, because this paper is unique. Assume beta is time varying. Most factor models, most studies assume beta are constant. So that's the difference. The difference might help us understand the difference of beta over time. So this is my first question. Now, here is the key. How to beat the market, or how to get extra alpha without taking systematic risk. Okay? And here's the portfolio optimization problem. So what you want is that you just transfer the factor that's orthogonal to all the beta. All the beta you have. You suppose you find number 20 factor. You got all the betas of 20 factors. I find the portfolio orthogonal to all the beta by my design. Here I assume I have 0 cost. Alternatively, you can make them have 1 cost of 1. So basically the same problem, just twisting the cost. Now, here is the portfolio you're searching for. You find that portfolio, give you the maximum power, uncorrelated with any systematic risk. And yet you want to say, what's the return? 0 by 30, or non-zero in practice. So that's really this optimization problem is trying to answer. Okay, Now look at this picture again. This beautiful picture again, as I mentioned earlier. Look at the right-hand side. That's results. Get a Sharpe ratio sizable. Okay, whatever you do, get this return this portfolio. Sharpe ratio could be 1.51. It can vary depending on your design. But the point is that statistically, with this procedure, you can get a factor that's orthogonal to any predetermined APT factor, and yet has significant Sharpe ratio, significant alpha. That's a good news for those of you who try to beat the market with good alpha. Okay, so that's really the message, the results. Of course, here I have one question. Now, in order to get this result, the paper uses machine learning. You say, where does machine learning play any role? It plays the role in estimating expected return on the stocks. Okay, so that's what they're using. Now then come to the question, how about if I'm using sample mean to estimate the stock return? Then I plug in that one exactly as what they did in their framework. In that case, do I beat the market or do I have extra return without taking any systematic risk? So that's, I think, probably interesting really to compare. Because this paper, now using the powerfully estimated expected return. Very good expected return. So just want to say the weight. In other words, the results are driven by their machine learning about the expected return, or something else. I think it's just interesting to tell the reason. Okay, so this is the second question. Okay. So this really sheds light on the estimation risk and the information role. Okay. Now, actually, also you look at the results. They find that the factor they identify from their procedure actually cannot be explained amazingly by the fund 3 factors. They didn't have their factor in mind, but the factor they identify has nothing to do with the main factors. That's really good news. That means APT, implicitly, APT factor capture those factors. That's what I can read. Because you have 20, 30 APT factors. The fund factors, just 4 or 5, those APT factors imply to them. That's why they cannot explain the return from your portfolio. However, the momentum can explain to some degree. How do we reconcile this? I think, in my view, probably this might be an explanation. In the APT, strictly speaking, we assume everything IID. There's no serial correlation. In the low momentum, there's a serial correlation. The portfolio you identified potentially has some correlation with good return. That's why momentum can explain your factor somewhat. I think that's the reason. Okay. Okay, so that's the explanation. Okay. Okay. So that's just summarize what I explained earlier. Then let's come to a question. I think it probably will be very cleaner. Why just get rid of momentum factor? Put momentum beta into your optimization, redo it. Then you can claim, oh, I got a portfolio orthogonal to any known factor. Name it. Any factor you know, it's orthogonal. Any empty factor you know, it's orthogonal. And yet, it has powerful return. That may be very clean. So just adding momentum, stick into data. Okay? Redo optimization. That's then really your factor really absolutely orthogonal to anything we know of. I think that's very impressive clean. Okay, now thinking this way, this is further. Can you do better? You already got some power factor, earn extra alpha, extra Sharpe ratio without taking the systematic risk. Can you do even better? Actually, there's one simple idea you can potentially. This is what I call, how about to iterated orthogonal portfolio? Now you've got a portfolio that's orthogonal to all the factors in the world and give you high Sharpe ratio. Okay? Now, how about I try to find another factor which is orthogonal to all the factors in the world plus a new factor I discovered right away. I redo my optimization. So that's what I'm talking about iterated. Okay? I redo it. Okay? Find a lot of portfolio. Well, this portfolio is orthogonal to everything we have come up before. It has hopefully the portfolio, if it has this positive Sharpe ratio, if it does, then what I can do, I can combine these two portfolios together. Then these two portfolios will have even greater Sharpe ratio. And yet, we're not going to do anything we know of. Then you make your story even stronger, more powerful. So that's really what I'm saying. Then you can achieve potentially the maximum Sharpe ratio. You got one portfolio guard. You keep find another one, we're talking to everything else. Then find the third one, we're talking to all the rest. Keep doing until you find the one that's no longer significant. Stop there. Then theoretically, the Sharpe ratio of your final portfolio, just the optimal combination of them. That will give you all the Sharpe ratio adds together. Then you get the maximum Sharpe ratio possible available in the universe. I think that's probably even more impressive. You make a story, strong story, even stronger. Okay, that's my last comment. Okay, to summarize, really, I think it's a really nice paper. It's thought-provoking, has intriguing results, and in my view, my interpretation is that it's consistent with the adaptive market hypothesis proposed by Professor Andrew Lo of MIT. What he says is that the market is adaptive, okay, evolving. But that's the hypothesis. Your paper is nice, providing the proof, empirical evidence for that. Okay, indeed, according to this hypothesis, really some factor will come, will go over time. For example, in my view, you can think about the 1980s, oil is very important, inflation was very important. Then started to die out for the last 20 years. Today, inflation become important again. So factors come and go. I've got new factors. COVID, probably everybody will agree it's a systematic factor. It affects everybody. Affects everyone in the world. So it's systematic. But surprising factor come into the APT. So I think your approach, I think it really is a way to show APT fail. I think in a profound way. Anyway, great paper. I will stop here.
I just need to clarify a couple of details, and then I'm going to ask my question. In these portfolios, how many holdings do you have, typically?
So we're using the whole universe of stocks as a typical holding. Like every stock is assigned a weight. We're discarding the 20th% of the smaller stocks to address illiquidity, but other than that, we're using the whole universe.
So you've got several thousand holdings?
Yeah.
Okay. And what's the time horizon that you're measuring these returns over?
So we're using 5-year rolling windows to estimate the expected return of the next month. And then we have results. I presented since 1974, 2021, I extended a little bit. But we also now are working on results since 1926, basically since the beginning of the CRISPR sample.
So you're basically forecasting the return over the next month?
Yes.
And are you rebalancing monthly then, or?
Yes.
Okay, good. So my question is this. It seems to me there's a paradox here, because you're creating portfolios that have no systematic risk, okay? So all that's left is the stock-specific return of each security, the alpha, the true alpha, okay? And yet these portfolios are consistently outperforming, consistently generating positive returns. So isn't there a paradox there? If you've got several thousand stocks all performing, most of them performing in the same direction regularly, doesn't that suggest that there's a missing common factor?
Yeah, so let me just clarify. So basically every stock has a different expected return dynamically, right? And what we're doing is we're dynamically choosing the stocks with a high expected return to be in the long side, and the stocks with the very low or negative expected returns on the short side. So it's not like there's a persistent differences in returns themselves. It's also not that all the stocks are moving in the same direction. And if you just think about it deeply, the issue is not that stocks move in the same direction on average, but rather that their innovations, that their variations are moving together. Even if you have like suppose the expected return of any stock is like constant. If there is no systematic variation associated with it, then you would still come up with a very high Sharpe ratio.
These are zero-cost long-short portfolios, right? So they're a bit academic in terms of trying to do this in practice. It's probably going to be very hard to have exactly zero-cost long-short. Once and I think Alejandro showed that once you have a unit cost portfolios or portfolios that are kind of net long, it's impossible not to have common variation. You're kind of in some sense load on the market in some fundamental sense. But the zero cost portfolio, it is pure alpha as pure as it gets, right? And that's what it is.
But if lots of stocks have got positive pure alpha at the same time, doesn't that suggest that there might be a common factor? Otherwise, I mean, if they're true stock-specific returns, by construction they are orthogonal to each other.
Yeah.
So if they're all moving in the same direction at the same time, that suggests that they're not orthogonal to each other, and therefore there's a common factor.
Yeah, so let me just mention a brief example. So suppose everything is just driven by the market portfolio. Suppose we only have like one beta, just the beta with respect to the market portfolio. If you go a portfolio that's exactly beta of 1 with respect to the market and subtract a portfolio that is exactly beta of -1 with respect to the market, then you'll cancel all the variation, right? If you agree with that statement, then the next step is simple. The next step is that I'm going to choose the portfolio with beta of 1 and the portfolio of beta of -1 with a specific excess returns. But that's it. Like the systematic variation is still completely canceled, at least ex ante and at least on paper. It's just that they still have a spread in excess returns. That was the slide I was showing where the difference in the expected excess return of the portfolio would just be driven by the alphas of the respecting portfolios. And maybe we can talk more about this.
Right. Just finally, I mean, in the example you gave, if you're just taking out the market factor, we know there are other common factors at work that affect returns. But you were claiming, I thought, that you'd taken out all the systematic risk.
Yeah, we do. That was just for like a simple question and answer example. We can continue the conversation. Would you pass the mic to?
Thanks. Great presentation, thanks. Just a couple quick questions. You stopped at the 20 first principal components and didn't continue onward. Did I get that right?
No, we use 50 principal components,
okay.
And yeah.
Did you try going beyond that?
Yes. So the issue is that you have to forecast all of this dynamically, and I was just extending the sample in this period.
So it just got too noisy in terms of the forecasting?
It gets too noisy in the sense that the 100 principal component is going to drive very little of the variation, and as a result, it's going to be very hard to estimate. So because we're doing a procedure when we forecast it, it just becomes like a flat return. If we, and this is a conjecture, if you use, for example, high dimensional data, you can, higher frequency data like intraday returns, you can probably get away with a higher number of portfolios. But if we were using 50 for the main table plus the 5 characteristic-based betas.
Yeah. One more question, if I could. You reform your portfolios monthly. Have you looked at how much the performance degrades if you rebuild your portfolios every year?
No, so it's a simple exercise. I mean, I think that's something that we should do at some point. And the thing that I would change is that instead of forecasting returns monthly, because now we're forecasting monthly, we'll just forecast at the yearly level.
Right.
I would imagine the results are in the similar vein with a smaller expected excess returns.
Yeah, it'd be interesting to see, because still with monthly, you could be picking up on a lot of reversal effects, things like that, right? I don't know do you know what your machine learning mechanism for forecasting is, what it's picking up on?
Yeah, so it's definitely picking a lot of past returns, a lot of book to market size, not always with the exact same sign. Like sometimes, the sign is time varying, and that's something that we're picking up because we're using rolling regressions. But the usual suspects are the ones driving the most variation. We also tried some exercise where instead of like using the characteristics like I normally use, we use the WRDS financial ratios, just accounting versions, and it also gets like some return predictability. Those financial ratios have less variation month to month, so the results should be similar in line, but it's something that we should definitely try. Thank you for the suggestion.
Thanks.
Well, one of the things here is, do you look at the size of the biggest W for long and short positions? Because when you're neutralizing 50 factors, I would expect some stocks would load very heavily. You're not controlling the W's, right? You're not constraining W's.
No, so just, informally, but looking at the maximum weights, they're like very, very small because we're using like thousands of stocks, and none of the individual stocks is loading heavily on anything. The intuition is that because we're forecasting both expected returns and betas, the variation is smoothed out at the individual level. So and also because we're by construction trying to get as maximal diversified portfolios as possible, we're like loading very, very little in each individual stock. So in this particular case, we don't think it's an issue, but we'll be happy to show some graphs deploying the specific weights for specific stocks.
I guess that's a follow-up question on the monthly rebalancing or monthly hedging. Have you looked at how similar your factors move from month to month, and like related to that, like any consideration given to like actual possible cost of hedging?
So for the betas themselves move very slowly because we're using like rolling windows and 1 year rolling windows, and then we're looking at the next month, and then we're using like a similar part of the rolling window and then looking at the next month. So the factor weights themselves are going to be very, very persistent, like extremely persistent. Like you can probably get away with this like a yearly level. Obviously, the factor realization themselves are going to be time varying and they depend on the specific market volatility period. But the weights of the factors would be like very persistent. That's for respect with the latent factors.
Sorry, I guess I missed that part. How frequently do you reestimate your factors?
So we're only showing the factors. It's monthly, but we're showing only the factors for like display purposes. Because in practice, what we're doing is we're just hedging all of these factors ex ante. Like we actually don't use them in the estimation procedure. We only make the betas with respect to those factors equal to 0. Monthly, but yeah, it's at the monthly level that we calculate the betas, but there's a long persistence because we use 1 year rolling windows every month.
Hi, I have a question about, I believe this is like slide 33 where you are showing a graph about the long short and the beta neutral performance of the portfolio performance against the market and risk free. I noticed that while your both beta neutral and long short outperform the market consistently, up until financial crisis, and since then it's like underperforming and also consistently underperforming the market. Do you have any insights into that?
Yeah, we think it's due to the decline in return predictability. Nick actually has another working paper studying that in more detail, and it may be because the institutional management just tries to exploit all of these predictabilities, so it kind of goes away. That's our best conjecture, but mechanically it's because the prediction power of just declines. Like there's just less predictability after the 2000s.
So my question is related to this time series regressions. So when we can see that when we move from these long short portfolios to these beta neutral portfolios, we can see that those factors did reduce their explanatory power. But we see this additional risk premium in the alpha. So I'm kind of curious, where does this additional premium come from? Is that risk-free? Because it feels like, yes, this beta neutral portfolio did reduce the risk exposure, but we get kind of like very promising more returns.
So just let me rephrase. So sometimes the beta neutral portfolio has higher returns than the long short portfolio. Is that the question? Why is that?
Yeah. Why would?
Well, if you think about it, sometimes the observable factors have like very bad periods of returns, right? So like depending on the specific sample, for example, the book to market hasn't performed well in the past 15 to 20 years. So if you have some exposure to that if you have some exposure to that, it's actually harming your expected excess returns and your realized returns. So if you hedge the exposure against factors that have negative returns, you actually get a higher realized return. So that's basically what's going on. You see like some factors that not only they're systematic, they also have like very low or like negative expected excess returns. When you hedge them, your return is going to be higher.